I forgot to use the AMGM inequality, and I didn't solve that question. I better see Eddie. I forgot that cubic functions had 3 roots, and I got that problem wrong. I better see Eddie. Hi, I'm Eddie. Did you know that you're a mathematician? Pythagoras says you are, and so do I. I believe every man, woman, and child watching this video is a hidden math genius. And that's why I'm here to help. Everybody, better see Eddie. Click on my channel for more interesting videos. Alright, that's enough for an intro. As you could probably guess, my name's Eddie, and I welcome you to my first video on solving math problems from all around the internet. Today we're going to look at a problem from the 2021 COMC contest. Now, since this is my first video, I need to say something important. I am by no means a mathematician or math expert, cause if I am, I wouldn't be making that intro. Anyways, I'm just a high school student. Now, you might ask, if you're just a student, don't you have better things to do? Why are you making this video? Well, first of all, video editing is one of my passions. Secondly, I guess you could say that I was inspired by other math YouTubers like Sri Brown, Blackpink Rappin, and so many more. So I was like, I have the editing skills, and I know how to do math. Why don't I make some videos on my own? So here I am. I hope that answers your question, and without further ado, let's jump straight into the question. So our problem goes, let m and n both be positive integers greater than 2. Each entry of an n by n grid contains a real number in the range between -1 and 1 inclusively. Here's an example of how you could fill out a 6x4 grid. The grid also has the property that the sum of the 4 entries in every 2x2 subgrid is equal to 0. A 2x2 subgrid is the intersection of 2 adjacent rows and 2 adjacent columns of the original grid, which is just something that looks like this. Question A asks us that suppose both m and n are equal to 6. Explain why s, which is the sum of all of the entries in the 6x6 grid, is equal to 0. For those of you who were able to find the solution, congratulations on your finding. And for those of you who didn't or just wanted to watch the video, fret not, cause I'll explain the solution right now. Since we already know that the sum in each and every 2x2 subgrid adds up to 0, we can try to divide the 6x6 grid into multiple subgrids to see if we can piece together any useful information. And once we do that, we're gonna quickly realize that our 6x6 grid can be divided into 9 2x2 subgrids without overlapping like this. And since there's no overlapping, we can calculate s, the sum of all of the entries, by adding up the sum in every one of these subgrids, which gives us a total of 0. Just proven, and let's move on to question B. So, question B gives us a 3x3 grid and asks us to prove an identity that s plus e equals a plus I equals c plus g. The authors of this question have kindly labeled every single square because they knew a random high school student is gonna make a video about this question in the future. Huh, just kidding. They obviously labeled the squares to avoid saying something like middle square or top left corner square or something like that. Anyways, when I first saw this question, I tried to use the same method I used in question A, but I failed because you can't possibly fit 2 or 3 2x2 subgrids in a 3x3 grid without overlapping. However, something hit me as I tried to draw the subgrids. If you were to fill out 2 subgrids in the opposite corner with colors, like in this case, you're gonna notice that E was colored twice, but A and I are not colored at all. Doesn't that remind you of the identity we're trying to prove? So, I went ahead and wrote down this equation, which makes sense because the letters in each bracket belongs to the same 2x2 subgrid and thus have a sum of 0. I then went ahead and rewrote this equation in alphabetical order. Since we also know that s, which is the sum of all of the numbers in this grid, is just a plus b plus c all the way to plus I tried again to rewrite this equation in terms of s. Afterwards, this is what I get. Let's rearrange the equation, and boom! We've proved half of the equation. Now, we still gotta prove the second half, which is S plus E equals C plus G. But this is easy, because we can basically do the same thing with a different set of opposite subgrids. I'm gonna leave this as a fun challenge for you guys, and let's move on to the climax of today's video, the final and last subproblem. Question C. Now, in COMC, the last subproblem always requires a combination of the techniques you used to solve the previous subproblems. Question C asks us to find the maximum value of S in a 7x7 grid. Wow, that sure looks hard. So, how are we going to find the maximum value of S? Well, remember that the number in each square ranges from -1 to +1? Yep, that was a condition of the problem. If we were to somehow express S in the sum of a set of squares whose values are independent from one another, we'll be able to make them equal to their extreme value and find the maximum of S. Now, I know this sounds confusing. And what do you even mean by having independent values? Well, take a look at this specific 2x2, which contains a +1 and a -1. The values of the two remaining squares we could not choose, but they will always guarantee to make the sum of the 2x2 0. If we change the value of the bottom right square from -1 to +1, do we also need to change the value of the top left corner square from 1 to -1 in order to maintain a sum of 0 in the 2x2? We don't have to, because we can just let the two remaining squares both equal to -1, and 1 plus 1 plus -1 plus -1 still equals 0. This means that for the two squares in the 2x2, whatever value we choose for the first square doesn't affect the value we choose for the second square. And therefore, their values are independent of one another. Whereas, if you've already chosen the value for the two squares to be 1, and you want to choose the value for the third square, you can only choose -1, or else the total sum will exceed 0. Until this moment, we've been using the 2x2 subgrid as the basic unit to separate the grids. We used the 2x2 subgrid to separate the 6x6 grid in question A, and we used two overlapping 2x2 subgrids to prove the identity in question B. But take a look at question C. We have a 7x7 grid, and using the 2x2s here would be just too inefficient and time-consuming. So we must find an alternative. Let me remind you that the reason we use a 2x2 in the first place is because the sum in each 2x2 is 0. What else has a sum of 0? A 6x6, which we proved in question A. So let's went ahead and use it. Similar to what we did in question B, let's put two 6x6 in opposite corners. Notice that now, instead of E, the overlapping squares is a 5x5 in the center. So, why don't we go ahead and label it as E? In a similar fashion, we can label these four strips as B, D, F, and H, and the four corner squares respectively as A, C, G, and I. Notice that S is still equal to A plus B plus C and all the way to I. Now, since the sum in every 6x6 is 0, we can basically write the same equation as in question B. Rearranging the equation, and we get S plus E equals A plus I. Let's subtract E on both sides, and here we arrive at this equation. And it looks like we're expressing S in the sum of a set of squares, except one of them is a 5x5, and the others are just 1x1s. To further dissect the 5x5, we need something that has a similar function with a 6x6, but smaller. You might be tempted to use a 2x2 here, but let me remind you that if we can prove a 6x6 has a sum of 0, we can prove a 4x4 in a similar way as well, since the 4x4 is basically just 4 2x2s stacked together. Now, let's do the exact same thing. We'll label the center supersymmetry as E slash, the 4 stripes as B slash, D slash, F slash, and H slash, and the corner squares as A slash, C slash, G slash, and I slash. They add up to E, the sum of the 5 by 5. Since a 4x4 has a sum of 0, we can write the following equation, and rearranging that equation, we have E equals A slash plus I slash minus E slash. Let's substitute E back in the original equation, and we end up with S equals to A plus I minus A slash minus I slash plus E slash. Now E slash here represents this 3 by 3. So let's do it one more time. Label each square as A double slash, B double slash, and all the way to I double slash. And I'm gonna skip this part since it's basically the same as question B. We arrive at E slash equals A double slash plus I double slash minus E double slash. Substituting it back to the original equation, and we finally have S equals to A plus I minus A slash minus I slash plus A double slash plus I double slash minus E double slash. Notice that every letter in this equation represents a single square. We have finally expressed S in the sum of a set of squares whose values are independent from one another, since no 3 or 4 squares exist in the same 2 by 2. Wait, don't celebrate yet. We still have one last step. In order to find the maximum value of S, we need to make the 7 squares equal to their extreme values. What I mean by this is that for every square we add, we make them equal to their maximum value, which is positive 1. And for every square we subtract, we make them equal to their minimum value, which is negative 1. After some simple calculations, we arrive at the final solution, 7, which is not surprising at all since there's literally 7 squares in this equation. And that is the 2021 COMC C2 explained. I didn't expect this video to be so long, and over the course of editing, I've made some drastic changes to the script of my video. So, I ended up spending a lot more time than I expected, and the video was overdue by a little. Well, since this is my first time making an educational video, if you have any questions or suggestions, please feel free to comment under the video. I'll definitely check it out. Thank you for watching this video. Take care and peace.